Okay, so in chapter 23, what we're talking about is inferences about means. We learned a lot about proportions, and what's nice is a lot of the same rules are going to apply. And the man who found this, his name was William Gossett, and let's see, he worked for Guinness Brewery in Dublin, Ireland, and his job was to make sure that the stout was of high enough quality before it was sent out. And so while he was doing this, he was using traditional statistics, looking at proportions in the normal model. And when he was doing this, he realized that his process wasn't making the type 1 errors 5% of the time like he had predicted, but it was actually 15% of the time. And so he was upset about this or baffled by this because he couldn't figure out what was going on. And so he ended up taking time off of work and went back to school to study statistics. And when he was doing that, he determined what was wrong, and he learned that for means you have to do something called a degree of freedom, degrees of freedom. And what's interesting about this little side note is that he wanted to publish the paper, but Guinness didn't want him to publish the paper because they were worried he was going to publish all their secrets on how they made their beer. And so he had to publish the paper under student X or student. And so now when we talk about a mean model, it's actually called the student's T model. And it was never named after him. Okay. And so if you look here, the blue right there is what a normal curve looks like. And here's the mean. And if you go 3 standard deviations out to the left or 3 standard deviations out to the right, that's where it about ends. And that's what a normal model does. But what he was finding with the mean is with 1 degree of freedom, it was a fatter tail and it didn't go as high. Okay. So then let's look and see what happens with 2 degrees of freedom. Again, the blue is the normal. The green is what 1 degree of freedom is, and then the red is what 2 degrees of freedom are. Okay, so if you notice, I'm a little closer to the normal model now with 2 degrees. And then the same thing's happening here with 3 degrees. I'm getting closer and closer to the normal model, so that's 3 degrees of freedom. There's 5. There's 10. It's getting closer and closer. And finally, 30, when you get to about 30 or higher, you're pretty much at a normal model. So again, Gossett had discovered that degrees of freedom is kind of what helped make the mean models more normal. And so the model that he discovered was the student's T model, which is a family of distributions that depend on degrees of freedom. Now, when we're working with means, the expression that represents the degrees of freedom is n minus 1. And remember, n is your sample size. So whatever you have is if you have 10 people that you sample, then it would be the degrees of freedom is 9. And so this is the degrees of freedom for means. Okay? All right, so there's some things that you should remember. And the smaller the sample, do you remember what happened to the tails? Yeah, the smaller the samples, the fatter the tails. Okay. Another thing that you should remember and recognize is that as the degrees of freedom, the DF, increases, did you notice that the center and the shape didn't really change? The center and shape stayed the same. But what happened was the spread got smaller. And yes, the shape did change a little bit and got skinnier, but that's because the spread was coming in. So it didn't go from unimodal to bimodal, okay? So it stayed the same that way. And then one other thing is, again, just it makes kind of sense, is that if you increasing the degrees of freedom, it's the same thing as increasing sample size. Because the degrees of freedom is taken from the sample size. Okay? All right, so what is nice about this, yes, it's another model, but it's a lot of the same rules that we've already had to deal with. You already know how to check if things are random. You already know that 10%, it's less than 10% of population. You know that. Independent, yeah, a lot of times we check if things are independent, and we just have to check to make sure that one mean doesn't affect another mean. So that's what the independent does. The new one that we have to get used to is we have to get used to that it's a nearly normal condition, okay? And so what you have to look for here is you have to look if it's unimodal, so there's one hump, and that it's symmetric. Those are the things you got to kind of check. And there's several ways to do that. You can look at the histogram or a box plot. Now, if you remember when we were looking at those different degree pictures, the higher the sample or the higher the degree of freedom, the more it looked normal. So kind of the rules kind of look the same. If you have a small sample of less than 15 or so, it's not exactly 15, but about 15, it should be pretty close. It should be pretty close to a normal model, and it should look pretty close to a normal model. If there's outliers or skewness, don't use this model. Don't use this method. Okay? So if you have a relatively small sample size, which means a relatively small degrees of freedom, you should not use it if you see extreme outliers or skewness. And we'll talk more about when is it extreme or when is it really skew. Okay? All right, so the medium size, which is about between 15 and 40, they work well. So the T models, which is what we're dealing with, work well as long as unimodal. They are unimodal and not skewed, so and symmetric. Okay? So again, if you see anything really drastic, really skewed, or really definitely a bimodal, it won't work for this. Okay? The last thing, a large sample, when you get above 40, and again, that's an about number, when you get above there, the T model is safe to use. And it's safe even if there is skewness. Okay? What happens here, though, is if it's skew, you can run this model. But if there's outliers, we're going to have to run it twice. We're going to have to run with and then run again without the outliers and see what happens. Because a lot of times outliers are really what tells us or gives us information about our data. Okay? All right, so down here, the margin of error, it may look a little different, but it's pretty much the same formula we have, except our critical point now is not z, but it's t to the n minus 1, which means it's the critical point for your degrees of freedom, because that's what n minus 1 is. Okay? So this is the critical point for T models. And again, what's nice is you already know how to find it. It's the exact same process as what we were doing with proportions. Okay? Over here, remember, SE is your standard error. And so this is the standard error for the population, which is the standard deviation for the sample. And we've actually worked with this a little bit, okay? All right, so now when you calculate your critical point for T, you're going to use the inverse T. And so we do it the exact same way as before, where if you remember, if I wanted something that was 92% confidence, we kind of draw our picture, and 92% is here. So that leaves 8% for both of these, so this is 0.04. So the only difference is here, now we have to use the inverse T for T model, okay? And so for this one, it would be the inverse T of 0.04. And then the second thing that goes here is the degrees of freedom. And so let's say our degree of freedom is 12. And so the calculator key again, go second distribution, go down to number 4. Oops, passed it. So it was 0.04, and our degree of freedom, I said, was 12. And so then that would give us our critical value point of negative 1.91. And remember, we just have been dropping the negative because we don't really want the negative, okay? All right, and so this is the exact same process as we were doing before, but now it's just the inverse t, and you have to use your degrees of freedom, okay? And so remember, that was the little formula some of you were remembering. It was 1 minus the confidence, so 1 minus 0.92, and then divide by 2, and that would give you what's there, okay?